Welcome to Zero Knowledge, a podcast where we talk about the latest in zero-knowledge research and the decentralized web. The show is hosted by me, Anna.
And me, Frederick.
So this week, we're chatting with Molly Mackinlay from Protocol Labs. She's the IPFS project lead, and today we're going to be talking about the IPFS 0.5 release. So welcome to the show, Molly.
Thanks for having me.
So we did an episode with Juan Benet from Protocol Labs back in, I think, November. And in that interview, I think we used about like a third of the interview to talk about IPFS and to set the groundwork of like what this is and how it's been used up to now. But the idea with this interview is to sort of say, like, okay, from that interview, and maybe even a little bit before that interview, what's been happening with IPFS? So I think to start off, it would be really great to hear a little bit about you, Molly, and how you arrived at Protocol Labs and how you started working on this project.
Absolutely. So I'm Molly. I'm the IPFS project lead. My kind of long-term background, I had a background in human-computer interaction, studied CS, and then went to Google and was a product manager at Google for 5 years. And while I was working there, I got really excited about building tools for teachers and students. I was on the Google Classroom team and spent a lot of time in schools thinking about, collaboration within the classroom and the work that people were doing back and forth. Realized that the way the internet was functioning, the way that the centralized model forced everyone to ship updates between teachers and students off to some distant cloud infrastructure in order to turn in assignments and do collaboration was like really broken. And we kept having to do all of this weird stuff in our mobile apps to try and get around that. And really at the end of the day, there just wasn't a solution. We, tried a lot of caching, but you just couldn't collaborate. Most schools have really terrible infrastructure and Wi-Fi. So that was kind of my aha moment. And when I started really participating, just really 1% time in the IPFS community, and that ramped up over the next couple of years. And I've now been working on the IPFS project for about a year and a half full time, and been the IPFS project lead for about a year. And so kind of my kickstart moment was like, the web should work offline first. We should have this local collaboration, and the efficiency of not having an intermediary or middleman or someone else that's, siphoning your traffic and then shipping it back out to people was kind of what got me excited initially. But there's a ton of other use cases that, I continue finding new ones where it's like, oh, that's, the content ownership story, where this actually is really relevant from an educational background perspective as well. But this question of who owns the content on the network, you kind of ended up in this classic struggle where the central app or entity would end up owning all of the data created by students and teachers, which was just this weird model, which didn't make any sense. Like the app would shut down or stop offering a feature, and suddenly teachers and students would lose their instructional data or not be able to access it anymore. They'd have to completely change their instructional model. And so that kind of being very beholden to some central service provider was a kind of nonsensical thing that'd grown in the internet in kind of the centralized application model I was excited about kind of coming to IPFS and changing.
That's so interesting that you came from this like educational or communication, this sort of like, that it was from a practical use case that you saw the problem that the internet had and then sort of dove in.
Totally. That's what got me jazzed about it.
So like Anna said, we had Juan on to talk about IPFS Protocol Labs in general, what the goals of the company are and things like that. And I think we've actually covered IPFS in various ways through many episodes because it is a thing that pops up every once in a while. But I think before we dig into the update and more specifics, let's do a general introduction again for those who haven't heard the content. What is IPFS? What is it for? What does it do?
Totally. IPFS is a peer-to-peer protocol and network. It relies kind of baking this core concept of content addressing into the web. When you look out into the network, the idea is instead of relying on central location addressing, which addresses content by where it's located in the network or who's hosting it, what domain it has, it instead addresses content by what it is. It's hash or fingerprint, and that allows you to load data from any peer in the network that's offering it, which means that when the network has a fault or gets divided or you happen to be offline, you can fetch content from anyone else in your subdivision of the network who has it. It also offers a lot of security benefits where you can truly identify what the content is instead of relying on some central party to serve whatever they want to you from the URL that you're accessing. And so we have this large distributed network now of hundreds of thousands of nodes that are constantly sharing data with each other, coordinating peer-to-peer. Anyone can join the network, and a ton of applications are built on top of that distributed file system.
Yeah. So it's a distributed file system that's content addressable. So in essence, it means that instead of going to google.com to get their website, I try to I wouldn't enter in, but somehow I get the hash of what the google.com website is. I enter that hash in, and whoever happens to have that can serve it to me. And I think a confusion point that I see a lot with IPFS is that everyone will have this content, but that's not true. Like, it's at the base, it might still be Google serving you that content. But if my neighbor went to google.com and got that content first, and then the default option is that they cache it and rehost it. But even if that wasn't the default option, they chose to cache and rehost, then I would just have to go to like my building's switch to go to my neighbor and then get the content. I wouldn't have to go to Google.
Exactly. And it's also, I'm a classic 10,000 tabs person. And so I'm very frequently reloading content that I actually already have open somewhere or I just closed 5 minutes ago. And so it's that case as well, where you may likely already have at least large portions of the content that you're trying to get from somewhere on the internet, whether it's a lot of sites using similar JavaScript or whether you're updating a package manager and only a few things have changed. By content addressing everything, you can very easily identify what content is new and only fetch the data that you don't already have. And so when you're fetching over IPFS, Bitswap, which is our transfer algorithm, will be like, great, I already have all of these blocks. I don't have to ask anyone for it. And then the new blocks that you need to get in order to update your package or load in the remaining bits of your website can get from anyone. And that could be, another computer in your same room where, you frequently have this thing where you're trying to transfer content between two computers. The fastest way I can find to send a picture between my Android phone and my iOS phone is like sending myself an email or syncing it to some sort of centralized photo sharing app, which is insane. And so just that model where you can very directly move content between the devices, not just that you own, but are within kind of connectivity of you. It seems like the way the internet should work.
Yeah. My favorite IPFS story, even though it's not necessarily super IPFS specific, but is someone setting up an IPFS server and routing all NPM traffic through that. So it was like in an office, someone set up an NPM server, and it saved them like tens or hundreds of gigs of download per day, because every time you do NPM install, it fetches every single package, even if you already have it.
Oh my God. That's crazy.
Even if someone else in the office has already run NPM install. So that's a nice use case. You could do the same thing with like a LAN cache server or something, but it's more fun with IPFS.
Totally. And it gets even worse the larger your packages get, right? So like imagine that you're instead, downloading lots of Ubuntu images or something like crazy.
Yeah.
So in the last episode, we did actually speak pretty much in depth about libp2p. I'm not sure if it makes sense to mention it here, but maybe we can.
We definitely can. Like that's the networking stack we use. So the two most related projects to IPFS that we actually joke that IPFS is a trench coat wrapped around IPLD, libp2p, and then kind of our UnixFS data model for files. So like IPFS is pretty much nothing. It's just packaging these things together such that we make a full file system. But IPLD is kind of how we construct the data, if you will, the model for CIDs and things like that. And then libp2p is the peer-to-peer network component of things that kind of has the DHT, has the pub/sub layer, has how you address peers in the network. And actually a lot of the improvements that we've made most recently are like on that intersection of IPFS and libp2p. And then the kind of remainder is, transfer algorithms and stuff like that.
So It's interesting, this like your background in education and this work about like students and and teachers sharing. Do you feel like IPFS reflects better what the vision that you had for what you would want? And I want to lead in a little bit with this. We mentioned this last time in our conversation with Juan about potentially doing like collaborative work on top of IPFS, this idea of like sharing things. And I'm wondering, yeah, I think we talked about it really briefly. I know it's not a particular IPFS project, but maybe we can talk a little bit about that.
Yeah, so there was a project back in 2018 called Peerbase that was something we were working on in, it was like the Dynamic Data and Capabilities group. So there was a working group that was thinking about how we could bring CRDTs into IPFS, especially there was kind of a misconception of like, oh, you can't do anything dynamic if you have static hashes underneath. If you have a static base, how could you make anything that updates quickly? Which I think is much less of a misconception now, which is great. So we had a group who was looking at that. They built this library, kind of like trying to be a Firebase on top of IPFS to just make building apps and tooling to make that a lot easier. And so they worked on that for a while, and we actually spun up a pretty decent, collaborative markdown editor that worked fully peer-to-peer called Peerbase, PeerPad, that's what it was. And that group was, pushing things forward. But at the end of the day, we realized a number of groups out in the ecosystem were actually also very interested in this problem and were taking it further than we could. So Textile started building a lot of their tooling around threads and now buckets, which are kind of doing the same thing but better than what we'd initially been experimenting with. So again, like append-only CRDT logs, and there's a number of other groups doing the dynamic app database work. So Orbit and 3box are other examples of groups that are kind of pushing that space forward faster than we could. So we refocused more on the core of the protocol, making sure that everyone could rely on a really stable core that was performant and made all of those dynamic use cases possible.
And what about that education idea? Like, do you see reflected in this what you had originally envisioned?
Yeah, I mean, I think there's far more than I'd originally envisioned. I was at the very top of the problem and hadn't looked all the way deep into kind of the challenges of unspooling things. There is actually a group that I found like 6 months into working on IPFS that was using IPFS for the use case I was talking about, where teachers and students, they shouldn't have to have a third party that's owning their data. So they were doing it for like data ownership for teachers and students so that you could maintain like, in a peer-to-peer model, both parties can have ownership of the data and host the data and make sure that no other organization can take it away from them or go offline or something like that. So I think there was a group in Australia or something like this that had started up a project like that. And I was like, oh, how I never thought of using IPFS for that use case. That's amazing.
Yeah.
The collaborative side of things, I haven't seen this applied to the educational world in particular, but I think the fabric that's being built, like the way the internet is working, I'm seeing that play out in a couple of other industries. I think probably hasn't made it to education yet, just because the UX requirements in a classroom where, say, you have 30 students and a teacher that's just trying to keep things under control, like the UX requirements there for it being like really easy to use and just very simple are really high. And we're still working to get to that point in the Web3 space right now. But I think there's a number of other tools in the IPFS ecosystem that are kind of approaching that from a collaborative kind of data updating nature. An example I'd call out that is kind of like the messaging side of things, or there's a group called Birdie that's working on kind of offline first messaging over Bluetooth. So you can just kind of have two devices next to each other, an Android and an iOS. And that's hard. Like getting the two of those to communicate over Bluetooth with all of the complexity of mobile stacks and APIs is like immensely difficult. They have a great article about like the spelunking it took to get these things to talk to each other. But I think that's one where kind of from a mobile perspective, you're offline in like a conference setting where the Wi-Fi's gone out and there's no internet, no cell connection, and you can just have two phones speaking back and forth to each other over Bluetooth using IPFS and libp2p. That was like, oh wow, it's happening. Things are lining up and getting into place for this to actually work.
That would be amazing at festivals, which I don't know if we ever get to go to those again, but I know
someday.
Someday.
I know Pierre, who writes Rust libp2p, he actually wrote Bluetooth transport layer for Rust libp2p as well.
That's awesome.
Sort of experimental. I don't know if he got it to work across devices.
Yeah, that was a super tricky
I think it was
part.
just Android. Yeah. But it's curious. I mean, we did it as this sort of thought experiment of like how do blockchains work if the internet goes down? Trying to build World War III proof software is hard, but that's what we're trying to do. But anyway, let's move into the main topic, I think, of this episode, which is this 0.5 release. It's curious to me just to hear a little bit about the history of how we got to this 0.5, because IPFS has been around for many years. I don't know even how long, like 10 years?
Not that long.
Something like that?
I think the alpha release was in 2015. So,
okay, 5 years. Yeah, a long time. And it's still not 1.0, but I still, at the same time, I get the sense that development has sped up, that things are sort of happening again. It was not really doing anything for a long time. Probably, like, my assumption was because Protocol Labs is basically happy with where it's at. But it does feel like it's sped up. And, what are some of the reasons behind that?
Yeah, so I definitely agree with the feeling that we're speeding up as a team and community. Definitely seen a lot of energy in the ecosystem, a lot of new groups coming in and pushing things forward. And as a team, we've also we feel ourselves that we've sped up from a development velocity perspective. Like the working groups pushing IPFS forward are awesome and executing really effectively. I'd say the biggest differentiator in kind of how we achieved that is thinking through the things that make us more effective and allow us to target changes that feel really large and really beneficial to people. And for this, it was actually kind of turning away from IPFS itself and then building what we're calling Testground, which is a new set of testing libraries and tools for simulating large distributed networks and then improving and iterating on them, which has allowed us as a team to really iterate much faster and prototype. When we have 100,000 node network, can be pretty difficult to in your brain picture what an improvement or change to the network would do. Like, will it actually work if we remove this timeout here? If we start putting records in this place versus where we did before, is that actually going to function? And so instead of guess and check, which was kind of what you have to do if you don't have any way of simulating things where you can reason about it on paper and then hope that you got it right, we built a full distributed testing environment so that we can simulate things like network latency, jitter, multiple versions in the network, nodes that are undialable, all of these things about how the IPFS network is in reality, and use that to make a ton of improvements to the protocol itself. And so that helped us kind of with the same team ramp up from a development velocity perspective. We also spent some time thinking about previously when you think about the teams that are working on IPFS and libp2p and other things, we were pretty separate, where we're each kind of focusing on the chunk of users and applications that were adopting each protocol. And for this one, we actually took the IPFS and libp2p teams and had them sit much more closely together and collaborate, because all of these challenges are the things that are making libp2p better for everyone. And so it's a faster feedback loop between people who are using libp2p in the wild and the team that's innovating and improving on it. And so I'd say back in beginning of 2019, there was definitely the DHT, it's not scaling to the new users we're seeing in the IPFS network. We need to go and make a number of improvements. And it wasn't until we were able to build up this tooling and really sit the teams more closely together that we could make really fast progress on landing pretty major changes to how the DHT was kind of formed and oriented. And so I'd say that was the difference there.
I love the way Protocol Labs, you'll build out tools that then become things in themselves, that you could almost release into the wild. It sounds like Testground is very specific to IPFS.
Not at all, actually.
But you say no.
Yeah.
Okay. It
so
could be bigger.
So there's definitely a way to build something like Testground that would be very purpose built. There's like, we can test the DHT and that's it and nothing else. But that's not how we like to build things. We think of things as more modular, more kind of multi-purpose. And we also knew that we would have a lot of other use cases where distributed testing infrastructure would be the thing that would help us execute. And so we had it in the back of our mind that we're going to want to test a lot of other things than just the DHT. We actually did immediately. The first thing that we tested wasn't actually the DHT at all. It was Bitswap. It was the transfer algorithm that we use in IPFS. And so good thing we didn't build something that was like very highly tuned for that use case because it wouldn't have been as reusable. And so, we're using different parts of Testground. So using less of the network jitter and more of the, many nodes kind of peering with each other and sending data back and forth. But actually, even since then, the libp2p team has been using Testground to do hardening for GossipSub. And so they've released another, I think, version 1.1 of GossipSub, which has a lot of improvements that were made using Testground and running these kind of large attack simulations and making sure that libp2p was resilient to all of those sorts of attacks. I think they'd sourced from like the Ethereum 2 team that's using libp2p, Filecoin that's using libp2p, and a couple of other groups of like, these are the sorts of things we need to be resilient to. And so that was, again, very multi-purpose, much more modular. Like you could even use it without libp2p. I think it's definitely not IPFS specific, and I think maybe even more general than libp2p. But the long-term vision, which I think is still a ways out there, but crazy idea going forward, is to actually think about not having any, like a single entity have to spin up Testground or run Testground regularly, but actually think about each node in the network as kind of a participant in Testground that's running test cases, which would allow you to do a lot of kind of more real
world testing.
Exactly.
Yeah.
And so that's kind of a future direction to continue exploring there. That'd be super useful.
Yeah, it would be cool.
Okay, you're using the acronym DHT. What is a DHT?
A DHT is a distributed hash table. It's how all of the nodes in the IPFS network coordinate with each other in order to route content.
We actually had an episode with Dominic Tarr from Secure Scuttlebutt, and we talked a bunch about networking and DHT specifically, and both problems that they solve and problems that they introduce.
Might be worth listening to. We'll add that in the show notes.
I'm curious to hear more about how, if one wanted to use Testground, like how do you actually integrate? Is it that you define your program in a Docker image and Testground launches Docker images, or do you have to like integrate with something or use some library?
Yeah, so there's a couple of different test runners. And so there's a local test runner, which uses Docker, and there's a K test runner, and I think also Docker Swarm. So there's a couple of different ways. Nice thing about that is it lets you start up locally using Testground and kind of doing fast development on your own computer, and then going out to the cloud and spinning up much larger clusters, being able to, scale this up to, I think the largest that we got for our DHT tests was 2,000 individual nodes, simulating like all of the realistic network configuration that we needed. But I think the GossipSub team got that even larger. I don't know how many thousands, but maybe 2 to 4,000 nodes, something along those lines. And so the kind of scale there, again, the things that it lets you simulate is real live large scale networks where you have all of these nodes that kind of follow. You write a test plan of, great, here's what the network's configuration looks like. These are the kind of sets of behaviors that I want nodes to do. And this is kind of the parameters for the network. So you can set things like, great, I want 50% of the nodes to be running this version of IPFS and the other 50% to be running a different version. So you can test interoperability. You can make half of the nodes undialable so that they won't actually respond to requests, which was really important. We've seen a ton of nodes join the IPFS DHT, and that's great. But then if they are participating as DHT servers, that's not so great because they start being like, awesome, I'll join the DHT, I'll be useful. And then people try and dial them and ask them where to go in the network to find content, and they don't respond to you because you can't actually dial them. And so this let us do a lot of those like test cases that we could run over and over and over again, fine-tuning those parameters.
What do you write the test plan in?
I assume it's in Go because everything we do is Go. And that's the lingua franca of the team. We also had the GossipSub team who was pushing this forward, did an integration with Testground and Jupyter notebooks. And so I think they wrote like a Python connector. And then from within Jupyter notebooks, they could do the set of configurations of parameters, which meant they could tune them really quickly and then automatically push the output of Testground into visualizations. So you could have, the graphs that were showing what latency looked like or how many nodes would join the network.
Nice.
You mentioned before Bitswap. Let's define what that is, because this is new, right? This is like coming with the release, as far as I understand.
So Bitswap itself has been around for a while. It's our data transfer algorithm. What's really it's new in that like a ton of improvements went into it. We've added a new message type. So previously, kind of the main way Bitswap works is you're trying to download a file. There's a large distributed network of nodes that could potentially give it to you, and you'll shout out to the DHT, hey, like, I want this root CID. So the root node of the entire Merkle DAG that makes up the file. And some nodes might throw that file at you, which, or that the block that relates to that root CID, which is great. And you'll add all of those folks to a session. You'll get a lot of those, hopefully, root blocks relating to that. And that's maybe not so great because now you've gotten the same piece of content many times, and that takes bandwidth from everyone to give it to you. But now you have a set of nodes, and you're able to resolve that root CID to like the next set of blocks that you want to get. And you'll ask those nodes for that content first. If none of those nodes have the next layer of blocks that you need, you'll go back to the DHT, ask them for the blocks that you're missing. Hopefully folks from the DHT will throw those blocks at you and kind of continue from there. The downside with all this is you'd get a lot of duplicate blocks because the way to ask for, hey, do you have this was like, give it to me. There wasn't a delineation between how those messages were structured. And so now we've added a new message type, which allows you to kind of identify whether someone has or doesn't have a block before they give it to you. Simple change makes a really big difference in terms of kind of throughput and how quickly we can scale to many different seeders and folks that are kind of trying to get a file from many people, and you can be much more intelligent about who you're asking for data.
In what you just said, I kind of can think of it maybe two ways, and I want you to tell me which way is correct. On one side, is it making it easier to fill in the blanks because you do less requests, you only request for the pieces that you need, or is it you only really make the request to those who have it? Which of those two is it?
It's more of the second one, where again, like you can check who has the data ahead of time before asking them to send it to you. And then you can choose one person to send you the data who actually has it and who then you don't have to ask many people that same request and then risk getting it many times or risk none of them having it and then having to ask a much wider network.
Cool.
I guess it comes at the trade-off of making more requests. Like you'd increase latency, but it doesn't feel like it matters much in this context, right?
It's more messages, but the messages are much smaller. So at the end of the day, it evens out to being much, much better and much faster. And kind of the additional, you can choose whether or not you want to use this message type. You can start directly at, hey, give me this block if you have it. And so you can tune it a little bit yourself as well.
Talking about the improvements, I think let's try to work through them and see what there is in this release. So improvements to Bitswap is one thing. You mentioned all this testing and iteration on the DHT, and we've actually talked about this topic on the show before about how DHTs have many problems, and I also know for a fact that it was kind of funny when we started using libp2p, when the two teams started using libp2p. It was a lot of occasions that we accidentally merged DHTs.
Oh man!
And so like I know for a fact that the IPFS DHT is incredibly polluted because we contributed to polluting it. Let's walk through those improvements. Maybe we start at the DHT.
Yeah, so definitely one of the challenges with the IPFS DHT is a ton of undialable nodes, a ton of folks sitting in the network who weren't being good participants in routing traffic. And so one of the big fixes there is to have nodes identify for themselves, am I dialable? Can I be a good participant in the network? And use that to configure whether or not they're going to serve and kind of be a router for DHT requests, or if they're just going to, consume the DHT that others are running, but decide, hey, like maybe I'm a browser node, maybe I'm a mobile node, maybe I'm behind a home firewall network and other people can't reach me. I'm not going to be a participant in the public DHT. And actually, as a part of that, nodes now run two DHTs. They run the one that's like the public network where they may be a client because maybe they're behind a home Wi-Fi firewall. And they also run a local one. It means that if you have like a home network, you can still like find other nodes and connect to them really easily if you're offline and do routing behind that network. So you might be a kind of more live participant behind the firewall versus being a client to the public network DHT. And so that's one of the areas. There was also just a ton of improvement to kind of the logic of how we did routing. So you want to get better nodes in the network that are helping route the content, but then you also want to do better dials, better logic about when to stop and terminate, how to quickly get to the end of your query. So again, kind of in a distributed hash table, everyone's kind of arranged in the network and you're trying to find the set of peers who have the records associated with the content you're looking for. As you're finding those peers, you want to make sure that you're, asking the right people and getting to them as quickly as possible. And so we made improvements there just in kind of efficiency to get there. And luckily at the same time, this also meant that we ended up making fewer dials by a lot, which makes things way faster and also reduces the bandwidth usage for every node participating in the DHT. And so those were a number of the changes that we made there.
Where did that, was that a sort of engineering task of just sit down, figure out where things are going, or was it here's a new piece of research on how to do routing in a DHT, or here's a new discovery algorithm, or like where does the improvement really come from?
Yeah, definitely. We did have kind of we spend a lot of time with a foot in the engineering world, a foot in the research world. This wasn't new research that we were kind of synthesizing and adding. It was more going back to brass tacks and, taking the existing DHT logic, the network that we had, and the research and kind of comparing and contrasting. We're like, great, here's the implementation we have. How does that line up with existing Kademlia? All right, what improvements and iterations do we need to make on top of that, given that we have this very large network with many nodes not being dialable? How are we going to respond to that? What improvements are we going to add? And from there, it was really kind of once we did that research census, analyzed our existing networks and got the testing set up, so we were able to get some baseline results about things like how many nodes were dialable and things along those lines. Then it was iteration of landing changes, seeing how they performed in our test cases, and iterating. And so it was mostly an engineering problem more than it was like a research problem. I would say like prioritization was where the research really helped. It was like, great, which of these changes is going to have the most measurable improvement to performance, to the metrics we care about, which mostly was how quickly can you find the content that you're looking for in the network. That was kind of also where research really helped. Kind of at the last minute, I think we switched from making sync DHT queries to async DHT queries, and that had a very large noticeable improvement. And so those are the sort of things where like looking at the ecosystem, the existing research, and just picking and choosing the exact improvements that were going to make the network better.
Talking about improvements, are there any other major improvements that we should be aware of?
I'd say like the two probably top headline improvements are the set of DHT improvements. So that's faster finding, faster providing of content that really flows in. There are a number of things people are excited about for IPNS, which is our naming system. So how you do mutable links in IPFS, which are getting a ton faster, but that's actually mostly based on all of the DHT improvements. IPNS was just a very heavy consumer of the DHT because you're trying to get many different copies of a record to make sure that you have the latest one, which meant you were doing a lot of DHT requests, and making the DHT faster and updating some of the logic there around IPNS, kind of how quickly it would stream back results to you. That's made IPNS both gets and puts a lot faster. And that was very slow and people were very unhappy about it. So we're glad to make that less painful for folks who are using IPNS. So that's kind of an important thing to mention in our tests. So we've been using Testground very heavily throughout for all of these features and improvements, but Testground tests for IPNS are just like astronomically kind of off the charts. When we're doing kind of our 1K tests where we have 1,000 nodes running the old DHT, trying to do like a normal test plan of like updating IPNS records and fetching updated content versus our new 0.5 release in the same test case, we see something like a 30 to 40x improvement in speed of like actually being able to do those gets and puts. And so that's kind of the order of magnitude we're talking about here in terms of making things better. That, again, it's a test case. And so that's with like a fully upgraded network with kind of not ideal conditions because we do model a lot of things around latency, but pretty, it's simulated. And so that's probably another thing to mention, even though it's not one of the top level features that people are most excited about, which I'd say are the DHT and transfer speed.
So you're working with Netflix. Tell us a little bit about how that happened, how that came to be, and like exactly what you're doing with Netflix.
Absolutely. We actually got connected with Edgar Lee, who works at Netflix back at IPFS camp last June. And he was really excited about a container deployment problem his team had, where they have this kind of distributed build process, and they were running into issues where they were hitting the API as kind of a bottleneck over and over again. It was adding a lot of latency to taking all of their kind of developer build process and putting it in the cloud. And so he found IPFS, started hacking on stuff, and came to IPFS camp with a really cool demo and benchmark of what if I took this build process and put it on top of IPFS. And so we got to talking at IPFS camp and kind of into the next like couple of weeks of like, ooh, this is really interesting. Yes, it seems like there's a lot of improvement here, but like we don't think this is hitting the theoretical limit. We think that IPFS can actually be a lot faster than Docker Hub because we're, like a little bit faster at that point, but it wasn't, we think, like highlighting the true benefit of going peer-to-peer. And so we actually started a collaboration with them and kind of Edgar and another engineer on our team started working on actually optimizing and tuning Bitswap for this sort of distributed container image challenge where you have many, many nodes that are trying to seed content from many nodes that have the content. Because great, you have the same container image, you want it spread across an entire cluster really quickly. And so Edgar built up a set of testing tooling called P2P Lab, which we were using before we actually got Testground off the ground to benchmark and test and improve Bitswap. Unfortunately, this didn't have any sort of like real latency or anything like that. All we could do was just optimize, which is what we did. And that's what kind of helped kick us into the improvements you see now as part of this release. And we made a whole ton of improvements there and got to, I think, like 2x faster back in like the October timeframe as we were working on this collaboration. And then we were able to get another 40% improvement just with like additional bug fixes, additional Testground tests that we were able to run. And so that's like, it just kind of keeps on giving. Every improvement we make to it is pushing forward. And Edgar reran the set of benchmarks against the previous version of the tests we'd made and the most recent one and saw like a significant improvement there as well. So it's super, super exciting and crazy how the stars aligned there. It was very much like folks coming and finding IPFS as a tool to solve a problem and then figuring out how to, continue integrating it in and working with us as we work to make it better to make those improvements and actually land it in a way that could be usable by everybody. And so it was very much like hand in hand and super exciting, right? Like, again, the thing that helps here is truly having the benchmarks that show, great, if you use Docker Hub, it's going to take 4 seconds. If you use IPFS, it's going to take like 1.7 seconds. Which one am I going to choose if I want my engineers to spend less time waiting for builds to compile? Like, clearly I'm going to use the one that's 1.7 seconds. And so that's like the sort of use case when you're working with like larger enterprises or folks that are kind of in the Web 2 model and not leaning into, I want it to be decentralized because clearly showing that value add and that use case is kind of what tips the needle.
The exact problem that they used you for, just to be clear, because like, when I first heard about this, I had the impression that like Netflix was somehow like using IPFS storage for others. And tell me like it's not storing the videos and distributing the videos. This is on the developer side. So this is, as a developer, you want to, compile Netflix.com like
the code for it, and you want to make improvements and changes to it. Instead of compiling it locally on your local device, you want to use kind of a cluster on your local cloud where you can spin up kind of like a Docker image and boom, run your test, and then boom, spin down the Docker image and get the test case back to you. But you have many engineers doing that all at the same time, all using the same sort of Docker image. Great. How do you make that really fast and really scalable? Instead of hitting a centralized Docker Hub API, you can have each node within the cluster send the data needed to spin up a new image.
I think it's an interesting, so it reminds me of that example I gave before of like running this to remove NPM install times.
Exactly.
But there's an interesting other aspect to this, which is I'm surprised that Netflix goes to Docker Hub at all, because if you look, I saw a talk once by the build system manager at Facebook, and they have like 2,000, 3,000 build machines, something like this. And they all run in parallel, right? They have one monorepo, and they're compiling and building a billion things and testing a billion test cases and everything. It's incredibly hard. And they use GlusterFS to have a distributed file system across all of these machines. So there's like one deployment of like the image of things that should be done, the job sort of, that gets distributed across these thousands of machines in multiple different regions, etc. And
so Netflix uses Titus.
They've had to like invent this whole system because like at their scale it wouldn't be possible for them to like have 2,000 machines reach out to Docker Hub and try to download. It just wouldn't work, right? So with IPFS as the middleman, instead of like re-engineering your whole system, you can sort of go with your traditional system, the thing that you would have at a small scale, the thing that you got used to when you built your product, and then you could kind of use the same workflow and the same pattern as you scale. You just introduce something like IPFS in the middle, and now you don't really have to re-engineer your whole workflow. You can just kind of do the same thing, but it's still faster.
Yeah, so Netflix uses Titus, which is their container management platform, and they built Titus and use that to kind of power all of their builds as well. And so that's also in the benchmarks as well. And IPFS is also faster than kind of their purpose-built Titus. I'm not certain how it works under the hood, but the challenge there around they do have like a Docker image container distribution challenge.
Yeah. And it obviously, like, anything's going to be faster than reaching out over the internet, because if you're in a server farm, you have like 40 gig links between machines that you can easily saturate, probably like with good NVMe storage. And so it's like, yeah, it's a whole different ballgame than trying to reach out over the internet.
Absolutely.
So that's an amazing use case, and congratulations on kind of having that partnership happen. I don't know if it's a partnership or a customer, but like, it's cool that happened. I think moving on, what else is in the release that might be interesting? Maybe in the realm of UX or tooling or something like that.
Yeah, so one of the things in this release is support for .eth links. And so something that's been growing a ton in the ecosystem, we've been seeing like a lot of traction and adoption for, is kind of these decentralized domain names. So kind of ENS and unstoppable domains, and a couple other examples where kind of instead of relying on DNS, groups are trying to use kind of decentralized alternatives. And so we've added support for ENS, and actually did a collaboration back in I think it was like the June-July timeframe, where we worked to spin up a set of bridging infrastructures, which is what resulted in the whole .eth.link URL, which enables you to load a .eth link without any sort of special extension or a special web browser or anything along those lines. And I think those sort of UX adapters or ways that everyone can get access to stuff that's happening in the Web3 world without having to intentionally opt in, it really helps increase the set of folks who get excited about things. And so this also comes at a time when it's just gotten a lot easier to put your website on the DWeb. And so we've seen this group called Fleek come into the space, and they've built effectively a Netlify for IPFS and DWeb sites. And that just makes it really easy for people to kind of take that first leap of like, okay, I have my personal website like in a GitHub repo somewhere. Can I deploy that to IPFS and just really easily get up and running? And so I think the sorts of things we're seeing now in the ecosystem are just how important those tools are, how critical it is for folks who are taking their first steps into this space and trying it out to get up and running and build confidence. And for everyone who's consuming those things, you don't want a site that only works in like one small context. You want something that's more broad. And so just trying to extend the accessibility of things happening in the space. And so that's, the reason we built the IPFS gateway was so that you don't have to go full into, I'm only going to browse Web3 or I'm only going to browse IPFS. It allows you to get rid of the chicken and egg problem of like which, IPFS has to be like the only thing being used before it becomes the default. Now it's just really easy for everyone to kind of from HTTP get access to IPFS sites. So like many people I think wouldn't even know they're using IPFS under the hood, but a site that they're browsing or kind of an application they love or anything like that can use IPFS through the gateway, and you'll just never know as an end user that benefits there. So
going back to your DNS work, I'm now curious, like I don't actually understand how IPFS and a DNS system works together at all. Like how does that work? Like what are they, like those are like URL names, they're names, it's a naming thing. Why is there a relationship there?
Yeah, I'm not the right person to explain about how all of ENS works, but I can talk to you about the specific project we did together.
Sure.
So ENS, Ethereum name service, allows you to kind of register, Molly.eth or whatever it is, kind of decentralized web identifiers. I think they commit them to Ethereum blockchain. And the integration we did was for the .link TLD. So you could do .eth.link, and that allows you, they run a domain name server, so a DNS name server that allows you to look up any .eth website when you append .link. And that kind of does that bridging process for you. It makes it pretty seamless for things to go back and forth. It also has an integration with the IPFS gateway so that when you configure your .eth address, you can be like, great, and the content behind this .eth address is, this IPFS hash, which is my distributed website. And so it fetches that and loads it from the gateway. And that makes it very seamless to like load the page and like, boom, you're on someone's personal static site.
I see.
Like this whole gateway, the whole bridging discussion is super interesting to me because if we take the .link example, you're you have a single point of failure in whoever owns eth.link. So you've re-centralized everything. And it's the same thing with gateways, and it's the same thing with something like Infura and MetaMask in the Ethereum world. And it's unfortunate to see that, we only have a couple thousand people who actually use the decentralized platform for real, and everyone else is going to the centralized service provider. So it's effectively still a centralized system, but at the same time, I know that we're not actually going to succeed in building a Web3 unless we build a bridge to Web2 world to let people cross over. So it's this really tricky kind of half-evil trade-off that we're centralizing everything, but we kind of have to bring people over.
Yeah. I mean, I'd call it like, it's an intermediate federated step on the upgrade path, right? So like lots of people run gateways, which is awesome and means that like, not any, like Cloudflare runs an IPFS gateway. There's like a ton of others. Infura runs one, Pinata runs one. There's a number of others. And so, again, you do, and this frequently comes in very useful where like, oh man, there's been a bad deploy for like 5 minutes. Suddenly X thing is down in the middle of a demo and you're like, great, awesome. I just changed it to the Cloudflare gateway and everything works fine. And so you do have that redundancy there as well. But I'd say having an upgrade path is really important. Like you can't, build for the future and not create ways for people to get there with you. And so kind of we see this as part of that journey. Realistically, like if you're building your personal website, or you're building kind of a front, like user-facing application where you're spending all of your time on the UX and thinking about how to do it really nicely, thinking about how to embed IPFS into that site, or, great, now it has to be a desktop application in order to be embedding a node. That just doesn't make sense. That constrains the problem and constrains people's creativity in a way that just doesn't work. The right solution, the real direction that upgrade path is heading, is having IPFS embedded in your browser, having it embedded in the tools that you use, having it embedded in your OS. And that's where we aim, so that the gateway wouldn't even be used if you already have a local node running. And so that's actually, we're making more progress towards that vision than I expected. So I'm maybe more on the optimistic side, that we're going to be able to get rid of these centralized stopgaps sooner than we kind of thought we would have to. Opera just released kind of default support for IPFS and Android. Kind of the continued browser upgrade path, next up is embedded Go IPFS node on desktop. And so those are the things that are coming a lot sooner than we thought they would. That we thought, pretty much half the web had to be on IPFS before you'd really be able to convince web browsers that, now is the time to add in default IPFS support. And so that's actually, I'm pretty optimistic about the upgrade path there. We're doing a chunk of work to add DWeb protocols to Chromium, which is kind of extending the work that Firefox was doing a couple of years ago, adding IPFS and DAT and DWeb and a number of other protocols to Firefox, and kind of working with Agalia and folks on the Chromium side to make that available, which then browsers can very easily toggle on and make accessible. And so I think there's a chunk of stuff happening there as part of the upgrade path that we're going to get there sooner than we think.
Cool.
Yeah.
That brings us to a really nice point in the interview, by the way, because I feel like we can go 1.0 now if we want to.
Sure. Yeah, that definitely did transition us into the road to IPFS. Yeah.
So this is IPFS version 0.5. So what is version 1? And when is version 1?
I have been joking a bit that IPFS 0.5 means we're halfway there. So to hold on, everybody.
5 years.
But no, I think the funny thing there is actually, the first half of 0.5 has been building up a ton of features. And by the way, we're 0.5, 0.6 is scheduled for 6 weeks from now. So we're going to be updating our versions much more frequently. But when you think about the last 5 years since the alpha, kind of it's been building all of this technology and tooling kind of up from scratch. And I think the next chunk of work, less than half, but the next piece that's needed before we can really put a 1.0 label on here and feel good about it is solidifying, condensing in on kind of the kernel of IPFS, what makes it go. We've seen a lot of groups kind of actually be experimenting with different subcomponents of the Go IPFS implementation, where great, these are all part of the IPFS protocol, but they're different kind of condensations of what's really necessary in order to have a minimum viable IPFS node operating on the network. And to kind of really call this implementation 1.0, we want to get down to something where it's small, it's stable, and it has future-proof interfaces. And so kind of the next chunk of work there is a little bit of an interface refactor, carving out the core kernel of IPFS and pushing that forward as great, this is a solid core that then you can have lots of plugins or experiments or other things that touch into this, but this central part of it is very stable. And so that's kind of the kind of next piece, I think, and actually relates pretty decently to the sort of work that would need to happen to have IPFS if you imagine, great, I want a Go IPFS node embedded in my browser, you're going to have to be thinking about modularization, minification, or, condensing things down, making sure it kind of uses very reasonable low amounts of CPU and bandwidth by default, and, all of those useful components. And from a timing perspective, that's a little bit more up in the air. I'd probably say sometime 2021 is kind of what we're aiming for. So not another 5 years.
Oh, cool. Do you work at all with Rust? We know that there's a libp2p Rust implementation, but that Parody's worked on. But is there anything else with Rust in IPFS?
There is. Great question.
What?
Yeah, there's actually a new Rust IPFS that the folks at Equilibrium Labs, who also work on OrbitDB, have started up a couple months ago. And it's awesome. It's making really amazing progress. And the Rust community in general, like, the folks at Parity, Pierre jumping in and helping work on this. There's some other folks in the IPFS community who are using IPFS on like IoT devices that are very excited for kind of a Rust implementation, which they can I think they have Android devices deployed in a mostly offline warehouse setting, factory setting. And so, great. As soon as like the core is there, they're going to jump on it and be using Rust IPFS. And so it's amazing just to see these implementations spring up from the community. I think libp2p at this point has 7 different language implementations across a lot of the different groups who are working in the ETH2 ecosystem. And yeah, getting to build on top of the shoulders of all of those amazing people who have got libp2p there. Again, IPFS is a trench coat around IPLD, libp2p, and UnixFS. So half of it's there if you've already got libp2p in your language. And we love seeing more groups come in and just start that up. It's really amazing, and I think like makes the community stronger.
I'm trying to picture what would it actually mean to have would it be a Rust client, a Rust IPFS client? Like how does that how do you have the 2 implementations of this particular? It's a protocol, so it's twice implemented, but they must speak to each other?
Yeah. So we already have a JS IPFS and Go IPFS. So luckily that means all of the interop testing already exists. So you can lean on that to do kind of conformance testing for a new implementation, which is what the Rust team has been doing. And so we do have 2 full implementations from the ground up. The reason that we ended up building the one in JavaScript was so that we could run it in the browser. And that was the use case that was designed for us. So you actually can. IPFS Companion does allow you to toggle on an embedded JS IPFS node. So you can do that in Brave today. You can go and kind of one click enable IPFS Companion and then have an embedded JavaScript node running in your browser. So that's super cool. But yeah, the big thing you needed kind of to implement all of the IPFS commands and then building that on top of Rust libp2p, which already existed. And there's actually been a ton of work that happened already on Rust IPLD as well by Volker on the IPLD team. So there were a lot of pieces and just bringing them all together and packaging them up.
Nice. I guess good luck with the next steps and the next releases. It sounds like you still have a lot of work ahead of you, but congrats on getting this far and on this release.
Thanks. It's been an awesome ride, and we're still only 50% of our way there towards our content routing goals. From a time perspective, I think we'll see where the network gets as soon as more folks have upgraded, because as more people upgrade to 0.5, the more pronounced the performance improvements will be. So we're still waiting to get some final numbers on what the metrics are going to look like. But we have another 3 months focusing specifically on content routing and making things better, and have some really exciting stuff planned for the 0.6 and 0.7 releases. So it's going to be an exciting couple of months.
Cool.
Thank you very much for being on the show. It was great catching up on all things IPFS and digging into some of these improvements.
Thank you so much for having me.
And to our listeners, thanks for listening.
Thanks for listening.